All right, so we started the op amps last Thursday. We started doing op amps, so we're moving more into op amps. And so last time we were able to identify. So last time. So being able to identify the configuration, op amp configurations. And then today we want to be able to determine, I'm not going to do this one, the output of a given op amp configuration. So those are our goals for today. So also note that you have a feedback assignment for tonight, but no homework this week and no quiz this week. So next week will be a homework and quiz. Yes.
When will the final exam grade be?
So I'm trying to have them done by next week. So I have a situation, so a heads up, there's going to be a guest lecturer who's teaching the other section will be here on Tuesday and Thursday for lecture. And then there will be an assignment for homework due on Thursday, and then your quiz will be due on Friday. And then another change is that I've opened up for quizzes. You'll have from Thursday morning till Friday night. So homework will still be due on Thursday, but for those that want to get homework done earlier, you can get that done and even start the quiz on Thursday. So there was a request to have that option.
Are the extra credit unit things, do they count, do you get credit after their due date or just before?
You'll get credit throughout the semester. So if you want to use those to help understand what you did wrong, I'm trying to figure out how to use Canvas to now post the actual solutions for your particular exam, but it's giving me issues. So if I'm not able to figure that out, I'll be moving those problems into the Unit 1 so that you can then go through those to find your answers for what you might have done incorrectly. And then, yes, you can get credit throughout the whole semester if you want to keep working on that to make sure you've mastered that so that when you take it for the final, you're even more prepared. Then you're welcome to. All right, any other questions? Okay, so last time we went through the op amp circuit. So how do you identify an op amp? Anybody remember? An op amp configuration. Okay. So you have to look at the inputs. After you have figured out how many inputs you have, what was the next step? Nobody remembers any of that, right? Okay. This is not the right one. Annotated. Okay, I'm going to copy this one. Okay, so first identify how many inputs you have, and then from there you want to identify whether it has feedback or not. Oh, this is not good. I think we're good. Paste. Okay, I do not know what happened to it. That is really weird. Okay, not going to do that one. Okay, so I'm going to write notes on here. Okay, so first identify that it has how many inputs. And then you have to determine if it's a feedback pathway or if it's just a switch. So switch or feedback. And then if one input you have three options: non-inverting, inverting, and a follower. So if it has feedback, then it can have one of these. If it's got two or more, it's going to be a non-inverting summer, an inverting summer, or a difference amplifier. And how do you know if it's non-inverting or inverting? If it's non-inverting, it's where? Positive terminal. If it's inverting, it's going to be the negative terminal. Same thing for the summer. All of them go into the plus and all of them go into the negative for inverting, and then the difference is one on each. So one will be at the plus and one will be at the negative. So this one, we identify the input. One input, it goes into the plus, so it is, which one? Non-inverting, great. This one goes into the negative, so it's inverting. Here we have three that go into the negative, inverting summer. Here's two, and one of each. Difference. And then this one is which one? It's a buffer or follower. Good job. And then here's my inputs here that go into the plus, non-inverting summer. So now we want to know, like, how do we determine the output of these? All right, so a couple of characteristics of the op amp. So one, I equals 0 into the plus and minus terminals. And then two, the voltage at the negative, I'm just going to call it N for negative, is going to equal the voltage at the positive. So once I find one of the voltages, I can set the other voltage to that value. So if this is 0, what is my voltage here? It would be 0 there if I had ground at the other side, but because there's a signal there, it's still going to stay Vs. So there's no voltage drop across RS, but so the voltage is the same on both sides of it. So if that's Vs, that means that this node is also Vs. There's no current in here, so the same current is going to flow from there to there. V out is this node, which is plus in comparison to ground. And if I take a voltage loop pathway that goes through here and then back there, that gives me my loop to ground. So plus to minus and plus to minus. So going from ground around this way, That's going to be a plus, plus, and then a negative over here. So plus I times R2 plus I times R1 minus V naught equals 0 gives me an equation for V naught. So to find I know the voltage at this node, right? This is all Vs. So knowing that voltage, I can find I by using Ohm's law. So Vs means that it's from that node in comparison to ground, which is where the voltage is across this. So that means Vs is equal to I times R2. And I can solve for I. Then plugging this in gives me V naught is equal to Vs over R2 times R1 plus R2. And that is my output equation for V naught. So depending on whatever my input is of Vs, I just need to add up the resistors R1 and R2 and divide by R1. And that's going to give me what we call a gain value for this one. So this one is, which configuration is this one? Non-inverting amp. And so this is my output expression of the V naught is equal to Vs over R2, R1 plus R2. So say R1 is 1K. And R2 is 1K. What is my V out? To Vs, correct. So it's just going to multiply whatever that input amplitude is and give me a gain of 2. So if I have 1 milliamp sine omega t, I get 2 milliamps sine omega t out. All right, does that make sense? So on this equation here, the summary of the op-amp circuit, it gives you this V naught is equal to this gain times Vs, and the gain is that R1 plus R2 over R2. So that's what that means.
And we could just use like these equations all the time.
Mm-hmm. Yeah. So let's look at so which one is this one? No. Okay, so inverting amp. So what do we know from this inverting amp? What is the voltage here? I heard somebody say it, 0 volts. So that means that this node, so this is my VP, and this is my VN nodes. So they're equal. So this is also 0 volts. No current flows here, and no current flows there. So those are the two things that, because of the characteristics of the op-amp, that's what you put in there. So that's where you get that knowledge, and then from there you can do the voltage loop to get the equation. So knowing that there's no current flow, this current is going to flow in this branch too. So both these are I have plus and minus. This Vs goes from here to ground, and this one goes from here to ground. So my loop in this case, when I go around, I'm going to go through VS, through this pathway, through there to get back to ground. So that's my voltage loop. Yes.
Why does the current flow the way it does?
Just arbitrarily called it that way. You don't know which way it goes. So you can just arbitrarily put it in there. So taking this loop, I get plus, 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 and then a minus. So plus VS plus I times RS plus I times RF minus V naught equals 0. And then I know this voltage here of 0 volts. So if that's 0, that is the same as, well, I can take a loop again. If you don't see it, this would be plus VS, and then a plus, and then I'm back to my ground that way. So plus VS plus I times RS equals 0. So my I then is a minus VS over RS. And then I can plug that in for those and solve for V naught. So V naught here is equal to VS plus a minus VS over RS plus RS plus RF. So getting a common denominator, this becomes RS over RS VS minus VS RS over RS minus VS RF over RS. And these two cancel. So then V naught is a minus VS RF over RS. And that is my output voltage for this inverting amp. So what if RF and RS are both 1K? So say they both equal 1K. V naught will equal negative VS, correct? So whatever I put in, I get a gain of 1, and then it inverts that. So the negative in this case just means that it inverts it, meaning that if I have a positive input, I get a negative input out. So what that looks like is if my signal is a sinusoid, my output is going to be a negative of that. So it's just going to invert it. And that's why it's called an inverting. So the non-inverting amplifier amplifies it. So this would be a output of inverting amp. And for a non-inverting amp, if that's my input, then this just amplifies it. So this would be the output of a non-inverting amp. Does that make sense? Okay. All right, so what's this one? Okay, so it is a inverting summer, correct? So the negative there, 3 inputs. What if I do superposition on this one? Superposition would put this into where it is, one of them is then just an inverting amp, correct? So superposition, I would ground these and just have one input. For one input in, if I was to solve this same way, I'm going to find that this is going to give me, well, this might be easier. So 0 volts here, that means there's 0 volts here. If I have 0 on this side and 0 on this side, no current can flow in any of these branches. With no current flow, same idea as before, the current would flow here to here, and we already solved that output. That one gave us that V out was a negative RF over R1 times V1. So it was this resistor over that resistor. So I can do this for each of these inputs, ground the other, solve for one, and then in the end, just add them all up. And adding them all up is going to yield a summation of all those. So negative RF over R2 times V2, and then a negative RF over R3 times V3. And this would be my output for this inverting amplifier. Does that make sense? So that's an easy way to solve this one, is just to use superposition, get one answer, and then see that it's the same for the other two and just add them up. All right, what's this one? Here we go. Inverting summer. Sorry, I didn't put that one on there. So this one was inverting, and this one is non-inverting. All right, so with this one, same idea of superposition. And with superposition, that means that one of these goes to ground. This one's harder to explain. But no current flows in here. So there's no current because we have 0 current here. So no current flows. So then this node becomes V1, and it's the same solution that I got before for the non-inverting amplifier, which is that V out is now a plus of that input, V1, and it was this resistor plus the R2 over the resistor that goes to ground. So this would be R1 over, or R1 plus R2 over R2. And then for the V2, it's going to be the same one. R1 plus R2 over R2. And that's going to be our solution for the non-inverting summer. What about this one? Correct? Difference amp. What happens when we ground this one? What does this turn into? Correct. It will be an inverting of this signal, So our output becomes a negative R2 over R1 times V1. So that's one solution. And then when I ground this side, what does it become? So if I knew the signal here, at this node, it becomes a non-inverting amp. So what is that voltage going to be there? So this voltage at that node is also the voltage across R4, right? No current goes into this one. How do you find the voltage across R4? It's what? Okay, I could do IR. So I put a current here. And then take my loop. Plus, this would be a minus, and then this one would be a minus. So plus V2 minus IR3 minus IR4 equals 0. And solving for I get V2 over R3 plus R4. And then the voltage at R4 is just that I times R4, which is V2 R4 over R3 plus R4. So now that voltage acts as the input to a non-inverting amplifier. So this portion of it is going to be that as my input. And then the non-inverting portion of this is the R1 plus R2 over this resistor R1. And that would be my answer here for this one. All right, questions about this? Yes.
Is it okay if we like don't understand this, but we just use the equations?
So part of using the equations is you understand where it came from. So you do have to understand which resistors are there and why, because they affect this amplification. Also understanding like what is impacting this solution. So if I so yes, it's okay to use the equations, but you do have to understand it enough to understand how to use those equations. So for example, what if I put a resistor here? Does that change the output at all? Are you saying no? Correct. Why? Any thoughts? Just because I told you so? Okay. So right here, this purple one, I put a load resistor there, RL. So when we solving this, we only calculated, we used the currents that were going through, back through the feedback loop. Does that current change if I put the resistor there? It doesn't change it because the voltage V0 is still there. And this is what the characteristic part of the op-amp is great for, because internally there's power that's going to be consumed there. It's going to supply out that voltage no matter what other resistor or other circuitry that you put on that V-out node. So in this case, RL does not affect the answer. V0 will still be those specific resistances. What if I add a resistor here. And my V1 actually goes through both these. How is R3 factored into the equation? Yes.
Yeah, would you just add it to the right side of the blue equation?
Where?
Like the R1 plus R2 plus R3.
So you would have R1 plus R3 on the bottom, and then plus R3 on the top. Because those two now have to be combined into one resistor, and they're in series here. Yes.
Why does it affect the front of the equation? Like, why does it affect that it's not part?
And there too. Thank you. Yep. So everywhere you want to make the equivalent resistances to know where they're affecting it. And then make sure, another thing I see when students just use the equations and don't understand them fully, is that you may mix up which resistor goes in where of the equation. So you have to be really clear as far as which ones are affecting it and where. Okay. What if let me go back to this one. What if I add a resistor in here? Does that change the output at all? It doesn't change it, right? Because that voltage was what we used to figure out the output. So that's still 0 volts. There's no current flow in there. And so the output's still going to be the minus Vs RF over Rs, meaning this resistor over this resistor. Yes?
What would it be if there was another resistor on the top, like where you did last time with VS, if there was a resistor there?
Uh-huh. Okay, so what would change in this equation? Correct. Did somebody say it over there? Rs plus R3 would be what you would change there. What if I add a resistor here? Doesn't change anything, right? Because there's still 0 current in that branch, it doesn't affect any of the voltage changes. Yes?
And then if you added a resistor on the feedback, it would be negative VS RF plus 3 over RS. What would that change?
Call that R4. Yep. Okay. All right, questions? So, no, do I want you to rederive this whole equation? You don't need to rederive them, but you do have to understand enough to know, like, oh, well, I found that because of the current flow. If I add a resistor and it doesn't change my voltage or my current flow, then it's not going to affect the circuit. All right, the last one is the voltage follower or buffer. So in this case, this node, which is my VP, is going to equal this node, VN, which equals what? What current's here? 0. So VP equals VS, which also equals VN. And then my node right there is V out. So V out is just going to equal VS. Right, this is all the same wire. So because it is the same wire and that characteristic that VN equals VP, there's my answer. So I don't have to do much more here. Yes.
Why would you use a follower and not just like draw a wire?
Good question.
Okay.
So okay, I'll call it VX and then VO. So say these are 1K. What is the output here for V out? It's going to be a half of VX, correct? So it's a voltage divider. It's looking for the voltage across this resistor, which is the same as V out. And so you can use a voltage divider of VO equals Vx times 1K over 1K plus 1K. And that reduces to the 1/2. Okay, so a lot of times you might have the situation where you don't actually, like this could be a load modeling whatever my load is. Most of the time you don't want that to change. You want whatever is kind of coming out to then go out. This part here would be, this could be VTH and RTH and represent a more complicated circuit that you've reduced down to 2 elements. If that's the case and you put on a load to it, you're actually only getting about half of the signal out of the circuit that you actually want. And so if we put in this buffer, and we put on a load here, it's a similar circuit, except for you put the buffer in between the output of whatever your more complicated circuitry is to this load. What's your output here? It just equals the same. So it creates this buffer where it's not going to load down or attenuate that signal from the more complicated circuit. Does that make sense? Okay, so this is the most useful part of this, is it will create that buffer in between there. It draws the power from the supplies that you've given it to maintain that V out stays fixed there. So that's where it got the name of a buffer. So it buffers your signal from one whole circuit to a load. So it's very useful in that respect. The other ones, the amplifiers are going to be when we have a small signal, we want to amplify them to get really big. So we can either amplify it in an inverting way or a non-inverting way. And that again will just depend on what my application may be. Or a lot of times it may not even matter. Whichever one is going to give me the least components. Summers are good for multiple signals when I want to amplify all of them. And then the difference amp is going to be very useful if I want to do a comparison. So those are kind of these building blocks for more complicated circuitry. A lot of times there may be like a mathematical expression that you actually are trying to implement. And so these can also be used to describe a mathematical algorithm. So you actually use them in an algorithm in a mathematical hardware way. So you can multiply the signals. The multiplication is your gain. You can add signals together, and they can each have different coefficients. So something like in a mathematical equation like 5x plus 3y plus 4z is going to be an amplifier that gives you 5 times the signal x. You're going to have an amplifier that gives you 3 times the signal y, and then another amplifier that's 4 times the signal z. And then you're going to add them in a non-inverting summer. So this would be something that could be created. Each of these would be a gain amplifier. So this is going to be an input of, or a gain of 5 for your input. So these would be inputs. These are all gains, meaning you're going to use a non-inverting amplifier for those. And then you're going to combine to give you a non-inverting summer. Or you can try and do the ratios correctly to give you those three ratios in one non-inverting summer. Sometimes it's hard to get the combination for just one amplifier. So a lot of times when you have things that may not work out well, you'll just amplify the signal itself first and then add them with a gain of 1 in that non-inverting summer. So you can create building blocks of algorithms. A lot of the times these are used in the hardware cryptography when you have a hardware box that's actually encoded everything into its own signal, sends it out, and then you have a box that decodes all of it. So these are very commonly seen there. All right, so another place you're going to see the buffer is at the input side. So this would be, what is this one? A difference, correct? A difference, and then all it has is the buffers on the input. And they're going to do the same thing as far as kind of buffer the signal coming from V1 and V2 so that it doesn't reduce the signal at all. So this is a very common thing that you're going to see also on the inputs to buffer it. All right, this is the last one you're going to see, which is called an instrumentation amplifier. So this is a combination of a difference amp and then if you notice here, these actually are a voltage follower, which is what we just saw on that input. And this one is a voltage follower because this doesn't actually connect to ground. What this one does is it allows you to control part of this. So your signal is still on the same signal or same wires that you saw in the previous one, which is going to be here and here. These act as your buffers. So this is your buffer and this is your buffer. And then we call it an instrumentation amplifier because of this resistor in the middle between those two. So there is, sorry, there's, okay. So the difference amplifier, you remember it was kind of this R2 over R1. And this one, because these are the same, is going to be R3 over R2. So R3 over R2. And then it's 1 plus 2R1 over RG. And then your Vn plus minus Vn minus. So you're going to most commonly see the instrumentation amplifier you can actually buy as a chip. You can then have control of that RG externally, and it will let you be able to put really small signals on your VN plus and your VN minus from sensors. So this is the most common time that you're going to use this is when you have outputs from sensors that are really, really small, and you need to compare those two together. So for example, like your strain gauges, you have two small signals. You're going to put those into these VN plus and VN minus, and it's going to give you the difference between them. So as you remember from those strain gauges, you wanted to know like how much is it really flexing back and forth. And so this is going to be a better circuit than the Wheatstone bridge in that it's going to amplify your signal along with it. And so you can get that amplification and that comparison as one. So a lot of times that's when this is going to be used, is when you have two sensors that have small inputs. Okay.
Where did the RF come from?
Oh, that was supposed to be RG. Sorry. Thanks. You're like, there's no RF in there. And yes, there is no. That was meant to say RG. All right. Questions? Okay. So again, understanding like, no, I don't need you to derive this equation, but then understand how to use this. So if I had extra resistors in here, how could I reduce that circuit so that I could use this equation with it? Would it change anything if I added a resistor here, RL? Okay, good. So no, it's not going to change anything. The equation stays the same. So V out still going to equal this. What if I added a resistor here? Purple. Does that change the output at all? No, because again, the current flow is still going to be zero there, so it doesn't have an effect there at all. What if I had a resistor in parallel here? One, I would need to do it to both sides so they'd be the same. Otherwise, my answer would be different. So I would have to add it to both of those. And then where would it change? I would have R2 in parallel with R4 there. Does that make sense? Okay. So you're just reducing whatever it looks like to reduce it so that it's a configuration like you know. So if you have a very complicated circuit before, like the op amp, a lot of times you can take the Thevenin and then just use the one resistor and one voltage source as your inputs.
If it's not perfectly mirrored from top and bottom, like let's say R4 is not on the top, do you have to do anything different, or does it just not work?
Yeah, so if R4 is different than the bottom, so these do have to be mirrored to get this equation.
Okay.
Otherwise, you have to use the full difference amplifier equation, which it was dependent on both side values. So the instrumentation amplifier, when you buy it as a chip, it will have those mirrored. And then if you're going to build it, you would want to mirror those so that you have more control and that the RG and the R1 is what's setting the gain. Does that make sense? All right, so let's look at this one when we have an AC input. I want you guys to take a second and try to determine what your output is going to look like. So in this poll, try and find the gain of this one. Call it gain 1, and then this one, say gain 2.
place of supply.
Wire there remember we found that limit as like 0 to input, so that wire there won't work because you have to have it's gonna be
I was looking at the equation, it's like the R3 here. Should be R3 over R1.
yeah. But you can't do that because physically
Okay. So it was just whatever.
well, you can't have different voltages on the same wire. So you can't have a 10 volt supply and then hook it up to 20 volt supply. So that's the same idea here with the op amp, but that's going to have the op amp at 0 volts.
Yeah, but the input is changed.
Correct? So when you have the feedback, you don't have feedback, it's fine, because then you have different tools on those and then will act as a switch. And when you have the feedback to it, if you connect that with that portion, you have another signal. But if you don't, you always have like filters where there's no connection on that.
And that wire's just directly. I know, but it doesn't matter, that just means it's wired.
I guess I was kind of confused, like, I get it that you can introduce it to add, but
Well, no, it's just supposed to be positive.
So there's an issue here. Did somebody saw it? Anybody else see it? What's the buffer look like? It has to go in the positive side. So this is actually something where you're trying to put 0 volts on that signal. So it's not possible. It's not possible. So instead, this should look like this. Okay, so this should be what you find. So for this circuit, then this becomes a buffer on the second part. And this is a inverting amp. And it looked like those that didn't put iPhone on there were able to figure out that this was going to be a gain at this location of 7K over 3K, and it's negative times Vn. And then that's also going to be what it equals on V out. So if my input is 1 here and minus 1, then this is going to be a negative. What's 7 over 3?
2 1/3.
Okay, I'll kind of put it down there. 1, 2, oh my. Okay, so it's gonna follow this in an inverting. This is gonna be, I didn't draw this very well, but that value will be 7/3. And this one will be a negative 7/3. As your peaks. Sorry, didn't quite get there, but negative 7.3 volts. Does that make sense? Seeing some yes? Okay, what if I put a resistor here? Does that change anything here? No change. What if I put a resistor here, a load resistor? Again, no change. What if I add a resistor here of 3K? This will change it to what? It will change your gain to a negative 10. Okay, good job. All right, is this making more sense now? You're seeing applications of it? Okay. All right, what is the gain for each of these inputs? Find this. So figure out the equation that your V out equation would be for this one. Put it here. So go ahead and work with your neighbor and write the expression for V out for these particular circuit with these values in there. Yeah.
All over the 10. No, wait, what? Oh, yeah, Adobe. I was going to draw on the break section. Like that is what it's simple as Oh, I didn't even like typing it out. Well, I took out the R3 or the R4, sorry. I put them in, so I did like the what's going on here? I thought it was higher to 2.3. I just did V over, so V1 over R1 plus.
So for those that answered, it looked like there was a consensus, which did look correct. So with this, you identify that it is a inverting summer.
Oh, yeah,
Inverting summer. And then from there, you're going to identify that it's this resistor over this one for the first one. So minus 10K over 4K times V1. And then for the second one, it's negative 10K over 2K, V in 2, minus 10K over 1K, V in 3, and that equals V out. So V out is a negative 2.5 V1, negative 5 V2, and then a negative 10 V3. All right, questions? Okay, so with this as a design part of it, if you have to go backwards and create the circuit from this equation, they have to have a common number in there. So that's why the 10K, it has to be something that's divided into 10K. So that's why I was saying sometimes it's difficult to get like a 5, 4, and 3. You have to get maybe a really large resistor. Okay. All right, so any questions about the material we've gone over today? Are you guys feeling more comfortable with op amps? Okay, they look a little scary, but they're not. They're just kind of this black box. You have to know that that has 2 inputs and 1 output. No current flow into the inputs, and internally it sets the voltage, whatever is at one terminal, it sets it equal to the other terminal. So if I fix one of those voltages, it does the other one if I'm in a feedback configuration. All right. Again, I'll not be here next week, so I don't have office hours either. But then I will be back the following week. And so do come still. There'll be a guest lecture. Homework will be due next Thursday. It will be on op amps, capacitors, and inductors, which are what you're going to learn next week. And then there'll be a quiz on the op amp for Thursday and Friday. And your discussion will be due on Thursday. See you in a couple weeks.